In this video, I will discuss some limitations of deep learning. Many of us wonder if AI, which sometimes can do better than humans, have common sense or not. In other words, we're asking why a deep learning model does not have common sense, at least as of now. So this can be understood using these two diagrams. So the first diagram represents the knowledge or the amount of knowledge and the type of knowledge that human brain has. And the second picture over here depicts in a way, illustrates the knowledge in a deep learning model. So in the first picture, what we see is that a human brain has a lot of common sense knowledge, not useful for doing some specific task, but a lot of common sense ideas. But we also have, so this is the amount of the bigger circle represents the amount of common sense knowledge that we have. And these projections here that we have, these projections represent the specific knowledge that we have. For example, people who have children may have better idea about how to take care of children, right? People who have a specific knowledge or expertise in a particular domain area may have a lot more knowledge, way more than common sense in that particular domain, and so on. However, a deep learning model looks like this. The amount of common sense knowledge in a deep learning model is almost none, but the specific knowledge to solve the particular problem in a deep learning model is very large or is very high specific knowledge, because the model is trained only to do a particular thing. Say, for example, recognize faces, right? Recognize faces, etc. This picture here is from a blog by Andres Karpathy. And in the blog, he discusses more in detail. But here, the reason I've included this picture is to highlight why people researching in the area of computer vision are not very happy with the current state-of-the-art computer vision. So let's look at this picture and consider some of the things that we as humans or with our mind, we can easily understand. So we can see that there are 3 mirrors in the scene. So some of the people are fake replicas from different viewpoints. So if this image was given to us, we know that these pixels here are fake pixels because this is a mirror showing somebody else. These are not real people. These are the people shown in these mirrors, which we understand are not real people. They're fake replicas. We can also recognize the face of Obama from just a few pixels that make up his face, even though the face is from a side view. We also recognize that there's a person standing on the scale, and even though the scale occupies only a very few pixels that blend with the background. So here everybody is just standing. It may be very easy for a deep learning model to maybe quickly guess that everybody is standing, but here we see that the scale that this person is standing on occupies very few pixels. It almost blends with the background. So if we did some sort of resolution lowering, then this would automatically, it would be very difficult to understand that there's a scale here. But we very easily understand that. Also, we understand that Obama has his foot positioned just slightly on top of the scale. So here's the scale, and you can see that Obama's foot is right on the scale. We also understand the working physics here, right? So Obama is leaning in on the scale, and this applies a force on it. Scale measures force that is applied on it, and that's how it works. That is, it'll overestimate the weight of the person standing on it. So we understand this, all the things that are happening. Obama is pressing on the scale, and this is eventually going to show up on the scale with a much higher value. And the person measuring his weight is not aware of Obama doing this. So this guy right here is unaware of what Obama is doing on the scale that he's weighing himself. And there are people in the back who find the person's eminent confusion funny. So because of this confusion, everybody in the background actually find this funny, and that's why they are smiling. So if we look at all of these things and ask, which of these things can deep learning do today? Not most of them. Probably recognizing Obama may be something that deep learning models can do today, but otherwise, rest of the things that we do so easily, deep learning models cannot do today. And this is exactly why people researching in the field of computer vision think that we are really, really far away from ideally where we would like computer vision to be at. Now, talking about the limitations of deep learning model is just a chain of simple continuous geometric transformations, mapping one vector space into another. So say we have an input image like this, which is basically an input volume, right? So we may have its width, its height, and certain depth. Then all that deep learning model does is transforms this into a different manifold and then maybe another different manifold and finally come up with maybe one scalar value that may be the probability or maybe a few scalar values that represent what this picture actually has. So all it can do is map one data manifold X into another manifold Y. And this is assuming that there exists a learnable continuous transform from X to Y. So from X to Y, we are assuming that there is geometric transformations possible, and we're trying to find it. So this is basically all that deep learning does. Furthermore, talking about the limitations of deep learning, a deep learning model can be interpreted as a kind of a program. Now, this is because eventually all that a deep learning model has is all the weights, right? So weights may be in the first layer, weights may be in the second layer, weights may be in the third layer, and so on. So if we can actually convert this into a program by saying, well, if my weight matrix multiplies with my input matrix, and if you get this, do this, if, and then basically all additions and multiplications, but we could technically convert a deep learning model into a program. But interestingly, most programs cannot be expressed as a deep learning model. So basically the point is algorithm is not equal to deep learning model. There are actually a lot of algorithms which solve problems so neatly and so efficiently that deep learning model cannot do it so easily. For example, say we have a given graph and we would like to find shortest paths, say all pair shortest paths or shortest path from one vertex to all other vertices. And let's say we want to use Dijkstra's algorithm to find the shortest paths. Now, Dijkstra's algorithm, despite being so simple and straightforward, can solve the shortest path problem very quickly and very efficiently. The same problem, if we create a deep learning model to find out the shortest path, then deep learning model we may not be able to come up with a deep learning model that actually does that. So for most tasks, either there exists no corresponding deep neural network that solves the task, that is, we may not actually have any deep learning model that can solve that task, or even if one exists, it may not be learnable. So in this case, say for example, we do have, or we can actually imagine a deep learning model, that takes a graph as input and produces shortest path, right? But maybe it is very, very difficult to learn that by creating data or by training it to that extent. So the corresponding geometric transformation may be far too complex, or there may not be appropriate data available to learn it. So the point here is that despite all the success of deep learning that we have observed, deep learning still will not be able to replace many of the neat solutions that we can obtain using algorithms. Now, continuing on the topic of limitations of deep learning, something that deep learning models cannot do is extreme generalization. What deep learning models do is actually local generalization, and what we humans can do is extreme generalization. Now, what is extreme generalization? Extreme generalization is an ability to adapt to novel, never seen before or experienced situations using little data or even no new data at all. So, this is basically abstraction and reasoning that we humans have the ability to do. Let me discuss this with an example. Say, for example, a 4-year-old boy is sitting somewhere and playing with fire, and suddenly he gets hurt by the fire. Then, even one experience of being hurt with the fire, it's sufficient for the child to learn that fire is dangerous. The child does not need to touch fire hundreds of times to learn that fire is dangerous. We have this ability to abstract and reason and learn from just maybe one single bad experience or one single good experience. This is extreme generalization. Now, deep learning models cannot do this. For a deep learning model to learn that fire can hurt, you have to really give a lot of negative examples, a lot of cases in which the deep learning model is hurt with the fire before it can understand this. So, local generalization, which the deep learning models do, is basically mapping from inputs to outputs. So, you have to have sufficient examples to learn these local generalizations. Let's look at an example. Say we would like to train a model to distinguish between various kinds of cats, right? So let's say we have a lot of data points and each of these data points represent, let's say, one cat each. Then even though a deep learning model, so given all of these cats, a deep learning model may be able to look at it and cluster them and understand that there are different kinds of cats in them, and actually even correctly predict the class for each of these cats, and given new data point also predict to what class or to what group that data point belongs to. Whereas we humans, we can cluster them, but along that we can also understand that overall these are all cats after all. So a deep learning model does not understand that those are all cats, whereas we understand that. One common question that many people ask is, do deep learning models have human characteristics? Now, we have a lot of characteristics as humans, but one fundamental feature of humans is our theory of mind. Now, this is something very interesting and a very specific topic within the psychology or the ability of human mind. This is our tendency to project intentions, beliefs, and knowledge on the things around us. More specifically, within theory of mind, we have various order states of mind. The most basic or first order state of mind is to think about ourselves. That is, I'm hungry, I want this, I want that, I want to go there, I want to do this, and so on. So we are thinking about ourselves. We are also capable of second order thinking. In second order thinking, we can think of other people. So here, this is, let's say, first person, and this is second person. For the first person can think about the second person. So this is second order thinking. And we can also do even higher order thinking, for example, third order thinking. In third order thinking, if this is me, I can imagine what you are thinking about me. So this is third order thinking because I can imagine you thinking about me. And this third order state of mind is something very unique to human beings. And we can even go higher order states, but such a capacity to project intentions and understand others' beliefs and our own beliefs and so on is a unique characteristic of humans. And obviously, deep learning models do not have that. Now, say we successfully train a model to generate captions to describe pictures. So, given a picture, a deep learning model can say whether somebody is riding a bike or somebody is driving a car and so on. The question is, does the model understand, when we say understand the way we humans do, the way we experience the contents of the picture and the captions it generates? So it can never do that. So that's another limitation of deep learning. Now, on the topic of whether or not deep learning models have human characteristics, it is important to, in a way, bring this up that deep learning models don't have any understanding of their input, at least not in a human sense. Understanding of the things around us in the world, for example, images, sounds, language, etc., is grounded in our sensory motor experience. We may not necessarily produce predictions or outputs, but it is all in our sensory motor experience. Machine learning models have no access to such experiences. They can't understand their inputs in a human relatable way. We can definitely get them, that is, our the deep learning models, to learn a geometric transform that maps data to human concepts, right? On a specific set of examples. This is very important. We can't, as of now or so far, train a very generic deep learning model. But this mapping that we can build is a simplistic sketch of the original model of our mind. So it is just a simple sketch of all the things that we can do. The one developed from our experience as embodied is. So let's look at this picture, and this in a way illustrates what deep learning models can do so far. So here's the real world, and from the real world we experience thing, and then we build our experience. From these experiences we develop abstract concepts in our mind. And now from these abstract concepts, whenever we have to label them or categorize them or present them, we simplify them and we exemplify them and create labeled data from the abstract concepts that we have. And then these labeled data can be used to train and build machine learning models. So we can use machine learning models to from these labeled data to make predictions, and then we can go back and verify whether the labels predicted by the model are true or not. But this doesn't necessarily mean that the deep learning models have understood the abstract concepts in our mind. It may not exactly match the mental model that the labeled data came from. And in the same way, it may not always transfer well to real world. And that is exactly why sometimes predictions from a model do not make sense when we look at them from the practical standpoint of being useful in the real world. Finally, to compare the human brain with a deep learning model, we know that roughly the human brain contains about 100 billion closely connected neurons. And then these neurons are connected using almost around 10 to the power 14 synapses in the human brain. So these are the connections between the neurons. Now, numerically, so our brain would be equivalent to roughly 10,000 VGGs. So I think the VGG network is roughly around 18 or so million parameters, right? So our human brain, if we had 10,000 VGGs, then the number of parameters would be similar to the number of parameters in the human brain. Now, it is definitely a big question whether or not 10,000 VGGs can do as well as a human brain, but in terms of number of parameters, this is the case.